Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, we, Group 2, will be presenting our group assignment BERT1333 Advanced Electrical Circuit with title Transfer Function and Board Plot. We were assigned as a group to solve a transfer function is question D and board plot is question E. Our group members is first, which is me, Nurulain Sofea binti Noor Hisham. Second is Aieenna Illeeya binti Nurzana. Third is Mohamad Razmer Ar-Ridzwan bin Mohamad Rosli. Next is Mohamad Faiz Adni bin Mohamad Yusri. And last one, Tengku Razin Danishputra bin Tengku Razali. For an introduction, the transfer function H omega of a circuit, the frequency dependent ratio of a phasor output Y omega, source voltage or current. Meanwhile, a board plot is a graphical representation of the frequency response of a system, showing how its gain and phase change as the input frequency variance. It consists two plots, one of the magnitude gain and one of the phase, both plotted against the frequency, often on a logarithm scale. Last, the plot display the magnitude in dB and phase in degree of the system response as a function of frequency.
Assalamualaikum warahmatullahi wabarakatuh. Today I want to explain the question D. It is from transfer function to board plot. The question is H omega equal to 50 J omega over J omega plus 4 J omega plus 10 to the power of 2. The question focuses on converting a transfer function into a board plot, which is a fundamental concept in control system and signal processing. The equation show the general process of simplifying a given transfer function H J omega into a form that is suitable for board plot analysis. By factoring the denominator and numerator into standard first order terms, we can identify the system poles and zero. They allow us to determine the key components of the board plot, the equation, the magnitude response, and the phase response. It is specific example. The transfer function is simplified and expressed in terms of normalized frequency components, making it easier to plot the logarithm gain and phase angle. Ultimately, the process helps in understanding the frequency response behavior of the system. The equation is represent a transfer function which is describe the output to input relationship of a system in frequency domain. The original transfer function is H J omega equal 50 J omega over J omega plus 1 J omega plus 10. The function has 1 0 at the origin because of J omega in the numerator and two poles at omega equal 1 and omega equal to 10 from the two terms in the denominator. To prepare this equation for board plot analysis, it is rewritten in a standard board form by dividing each term in the denominator by its poles frequency. H J omega equal to 50 J omega over J omega plus 1 J omega plus 10 equal to 50 J omega over J omega over 1 plus 1 J omega over 10 plus 1. Then we factor out the constant value to simplify further. 50 J omega over J omega plus 1 J omega plus 10 equal to 0.125 multiply J omega over J omega over 1 plus 1 J omega over 10 plus 1. The final simplified form is very helpful for plotting Bode diagram because each components of the equation correspond to a known behavior. The terms j omega 0 at the origin increase the slope by plus 20 dB decrease and adds plus 90 pace. In terms j omega over 1 plus 1 pole at 1 rads decreases the slope by negative 20 dB and subtract 90 degree pace starting near the frequency. The terms j omega over 10 plus 1 pole at 10 radians does the same but starts affecting the plot at 10 radians. The constant 0.125 give an initial gain offset of 20 log 10 0.125 equal to negative 18 dB. The standard form made it easier to draw both the magnitude and pace Bode plot by breaking the function into smaller parts that we understand well.
Today I will be representing a bit about magnitude and Bode plot. Let's begin with the given transfer function is h omega equals 0.125 multiply with j omega divide j omega over 4 plus 1 multiply j omega over 10 plus 1 power of 2. This function looks like complicated, but we can simplify it to make it easier to find the magnitude. To find the magnitude in decibel, we use the formula is HdB equal 20 log 10 Hj omega. After breaking it down using logarithm rules, we get HdB equal 20 log 10 0.125 plus 20 log 10 omega minus 20 log 10 1 plus omega over 4 power of 2 close bracket power of 1 over 2 minus 20 log 10 1 plus omega over 10 power of 2.
Now, let's look at the Bode plot. In this case, we are given another transfer function. This function is used to create the Bode plot shown in the graph. Let's break down the components one by one. The numerator 15j omega will increase the slope by plus 20 dB over decade. The denominator has two parts. The first one is j omega plus 4 will decrease the slope by negative 20 dB over decade starting at omega equal 4. Second is j omega plus 10, the power of 2, will decrease the slope by negative 40 dB over decade starting at omega equal to 10. This is how we sketch the Bode plot, by identifying where the slope change and by how much based on the components of the transfer function.
Assalamualaikum and good day everyone. Today I would like to present something that I just learned, which is the Bode plot. For specifically the phase plot for the graph phase. As we can see on the left side, that show a graph that known as a Bode plot. So basically, what is a Bode plot? A Bode plot is actually made of two parts. So for the first part is the magnitude plot, and the second part is the phase plot. Usually the phase plot show two curves. So today we are focusing on the phase plot, which show how the phase of a signal changes with frequency. It tells us how much the signal is delayed or advanced as a frequency increase. So the first curve is the magnitude plot. It shows how strong the signal is at the different frequencies. The second curve is the phase plot. This shows how the phase angle of the signal change as the frequency increase. So move to the right side. As you can see, there are some equation. They are used to calculate the phase angle. So let me explain the equation. For the first part is j omega plus 90 degree means you have term is just j omega if give the phase shift of 90 degree, positive 90 degree. For the second part, 1 plus j omega over 4 is give a phase of negative tangent power of negative 1 omega over 4. For the third part is 1 plus j omega over 10 the power of 2. So if give the negative 2 times power of negative 1 omega over 10. So when we combine everything, we get the total phase shift, which is show as a theta, which is 90 degree negative tangent power of negative 1 omega over 4 negative 2 tangent power negative 1 omega over 10. As we move the left to right, mean as the frequency increase. So the phase start from positive 90 degree and drop down. It shows how the system react to the signal of the different frequencies. So in a short, graph show how the angle or the timing of the signal change across the frequency. Even though it may look complex, we need to just remember the each component of the transfer function adds or subtract a specific phase, and the phase plot show the overall effect. So in summary, the phase plot in a Bode diagram helping us understand how the phase of a system change with the frequency. This is very important in electrical engineering, especially to analyzing system stability and controlling. So that's all for me. Thank you for listening.
My name is Tengku binti Razali, matric number B123410449. Today, I will be explain how to obtain the transfer function from the Bode plot step by step. So first, we need to find the gain constant, which is we call K. Okay, we can use the formula 20 log K equal H in dB. From the plot, we can see the magnitude is 20 dB. So 20 log K equal to 20, K log K equal to 1, and finally we can get K equal to 10. Look the slope of the plot and identify the important frequencies. First, from 1 to 5 radian per second, the slope is positive 20 dB per decade. This is mean that a simple 0 at 5 and we write is 1 plus j omega over 5. Then from 5 to 10, the slope become the flat, and at 10 radians per second, the slope drop by 20 dB per decade. This tells us the simple pole at 10, so we can write 1 plus j omega over 10. Lastly, from 100 onward, the slope drop again. This time by 40 dB per decade, which is a stronger drop, meaning there are double pole at 100. So we add 1 plus j omega over 100 square. Now that we have all information, we can write the transfer function. In general form, it looks like this: H bracket j omega equal K times bracket 1 plus j omega over 5 close bracket divide by bracket 1 plus j omega over 10 times 1 plus j omega over 100 square. Finally, we substitute K equal to 10 into the equation, and we get H bracket j omega equal 10 times bracket 1 plus j omega over 5 bracket divide by 1 plus j omega over 10 times 1 plus j omega over 100 square, and that you're the final answer for the transfer function.
As a conclusion, a transfer function represents the relationship between the input and output of a linear time invariant LTI system in the frequency domain. The Bode plot is a graphical tool that shows how the magnitude and phase of this transfer function vary with frequency. By analyzing the Bode plot, one can easily identify key characteristics like resonance, peaks, bandwidth, and cut-off frequency. The transfer function of the system or filter is shown in the Bode plot for the conclusions, providing a comprehensive perspective of the system frequency domain. Both the system phase and magnitude at various frequency can be used to characterize this response with regard to a range of frequency in the input signal. This magnitude and phase computation offer a more precise efficiency of the system's operation. So that's all from our group. Thank you.